Hello, welcome to Econometrics Melody. In this video, we'll discuss about the correlation coefficients or the correlation between the random variables. We know how to calculate the expectation of the random variable in case of discrete random variable, as well as the expected value of random variable x in case of the continuous random variable. Similarly, we can calculate the variance of the random variable x, as well as the variance when the random variable is continuous random variable, and this one is when the variable is discrete random variable. Similarly, the variance for x, we calculate it using the expectation, making use of this formula, and its expanded form, it is equals to, that is expected of x square minus expected of x whole square. Similarly, covariance of xy, this is equal to this, the product of the deviations from mean along with the probability, and we sum it from 1 to n. And similarly, in terms of expectation, we take the expectation of the product of the deviation from the mean of the respective variables to calculate the covariance between x and y. And in its expanded form, covariance of xy is equals to expectation of xy minus expectation of x into expectation of y. And in today's topic, we are going to deal with the correlation coefficient. So we need to calculate the covariance of xy and the root under variance of x into variance of y. This is going to give us the correlation coefficient between the variable x and y. And we know that the correlation coefficient is greater than equal to -1 and less than equal to 1. Therefore, the correlation coefficient, it ranges between plus and -1. Now, based on this formula, let us see some of the property of the correlation. Is the correlation coefficient is the function of covariance and variance. So the property of correlation coefficient depends on the properties of these parameters, covariance of xy as well as the variance of x and y. Now let us explore the first property, that is related with the correlation of any random variable x and the constant variable called b. So this is equal to, let us use this formula, covariance of x b divided by standard deviation of variance of x and standard deviation of y. Y here is b. So in our earlier video, we have seen that the covariance between a random variable and constant, that is equals to 0. So this should be equal to 0, whatever term we have over here. So this is equal to 0. Therefore, we say that the covariance of a random correlation of a random variable x with any constant variable b, that should be equal to 0. Now let us see another property that is related with the scaling of the variables. Let us say we want to calculate the correlation and we want to scale the variable x by a and variable y by b, and we are going to calculate the correlation coefficient. Again, let us put it into their formula. So the covariance is proportional to the product of the scale. So we have seen this property also in our earlier video. And covariance of xy, similarly, variance of ax is equal to a square variance of x, and very similarly we can write it as b square variance of y. And a square, so outside of this square root we get a, and from here we get b. So ab they cancel out, and we're left with covariance of xy divided by root under variance of x into root under variance of y. This is again equal to the correlation between x and y. So we see that the scale is also not going to affect the correlation, so the correlation coefficient is independent of any scaling. Now let me explain this property by the help of example. We have a random variable called x and another random variable called y. We can calculate its covariance, or correlation of xy. We can always calculate it, and we know it. Now let me scale this random variable x by, let us say, 5 times, and let me scale the random variable y by, let me say, 6 times. And if we calculate the correlation coefficient of this 5x and 6y, this should be also equal to, if the correlation coefficient between xy is, let me say, 0.7, then this should also be equal to 0.7. So the scaling of the variables correlation coefficient does not change even if we scale the variables. Now let us see another property. What happens if we shift the origin? How is correlation going to respond to the shift in the origin? So let us say that we want to calculate the correlation of ax plus b and another variable called cy plus d. So here variable x, random variable x, is first scaled by a and then its origin is shifted by b, and variable y is scaled by c and its origin is shifted by d. And let us put it into formula. And as we have seen in our earlier video that the covariance is indifferent of this shift in the origin, and it is proportional to the product of these scalings. So this is equal to AB covariance of x and y. Also, the variance is also not affected by the shift in the origin, but it is proportional to the square of their scaling. So this is equal to a square variance of x and c square variance of y, all divided by, so square root of a square is a and square root of c square is c. AC we are left with, so this is AC over here, and AC and AC they cancel out, and we are left with again correlation between x and y. So the scaling and both the scaling and shifting of the origin is not going to affect the correlation. In other words, correlation is indifferent of the scaling and shift in the origin. Let us explain it in terms of the example. So we have a random variable called a and b in its original form, and we can always calculate the correlation of a b. Let us term it as x, and we are going to scale the variable a by twice and changing its origin or shifting its origin by 5, and we call this as variable c. And we have another variable called d. We are going to first of all scale this variable b by, let us say, 7, and then we are shifting its origin by 10. So if we get the observations, and if we calculate the correlation between C and D, so this should also be equal to the correlation between A and B. So the value of this should also be equal to X. So this is indicating that correlation coefficient is indifferent of the scale or the shift in the origin. Now let us say another property that is related with the independence, and let us say that variable A and B, they are independent. And we know that for independent events, probability of A, B, so the probability of the intersection is equal to the product of their individual probability. We have seen this, and the expectation counterpart of this relationship is that the expectation of AB, so of the variable AB, this should be equal to the product of their individual expectation. And we have also seen that if this is true, then covariance between the independent events, this should be equal to 0. We have already proved this. Now let us assume that the random variables a and b, they are independent. So let us calculate the correlation coefficient of the random variables a and b. So the formula that we have is, so as we have already explained, that if two random variables, they are independent, then their covariance is equal to 0 due to this property. So we take it as 0, but despite of the variance of a, b taking any numerical values, as the numerator is 0, this is also equal to 0. Therefore we can say that for any independent events, their correlation coefficient is 0. So this is it for this tutorial. Thank you very much for your time. Thank you very much, Econometrics Melody.